Hello, and welcome to this wireless telemetry lab and tutorial. In this tutorial, I'm going to be providing a brief overview for how to do parameter sweeps and optimizations in CST. Before I do that, though, I'd like to give some context for what we're going to be optimizing. So here we have a model of an antenna submerged in a beaker with egg white. Nice and simple. So the way that this is constructed, this is modeled to be a 250 milliliter beaker, something you would find in our lab. And there are a couple of parameters of interest to us. So the first one is insertion depth. This is how far into the beaker the antenna is inserted. In the case of this model, the insertion depth was set at 50 millimeters. So it was inserted 50 millimeters in from the top of the beaker. Second one is the parameters that define 50 milliliter beakers, which you can find those parameters for all sorts of different sizes of beakers as needed here. So things like the diameter of the beaker, the height of the beaker, and then the thickness of the glass of the container. And then the last thing of interest, just to make this model and simulation a little bit more user-friendly, there's a variable I defined called fill, and this refers to the fill factor, or how full the beaker is with whatever the substance is, in this case egg white. So this is simply a decimal representation of a percentage. So in the case of this model, the fill factor was set at 0.7, meaning that it's 70% full. This is designed to be able to better match the simulation to the real world experiments we're going to do. It's very unlikely that we would take the time to fill this 250 milliliter beaker all the way to the top with egg white. And so the fill factor allows us to say, how willing are we to fill this beaker, and fill it accordingly, and then do the simulation accordingly. Anyway, the other thing of interest is now more specifically to optimization. So in CST, you will optimize on a variable, meaning when you run either a parameter sweep or an optimization, you're going to optimize a specific variable of your model. This is why it's so important to parameterize your model. So for example, the thing that makes our antenna unique is these two gaps that are cut in. So let's say that we want to parameterize these gaps. So the way that we would do that, actually in the simulation software, is we would go to the simulation tab. We have two options that we're going to discuss. We're going to discuss parameter sweep and optimizer. I'm going to start with parameter sweep, which is in this solver section of the simulation tab. So when we go to parameter sweep, you can define a sequence. I've already defined a sequence here. So remember I said, let's say we want to optimize this gap variable. So you'll choose your parameter that you want to optimize from a drop-down list. The type of parameterization is most likely a linear sweep, but you have other options at your discretion. You'll select a range. In my case, I did between 0 and 3 millimeters, and you can define it either doing a step width like I did. So you'll go from 0, 0.5, 1, 1.5, etc. if you do step width, or you can say, I'd like to define a number of samples within this range. We're going to do step width. We're going to stick with step width rather. And so then we end up with that sequence. So what does this really mean? What does this do for us? So what will happen is in CST Microwave Studio Suite, it will run a series of simulations varying the gap size. What you'll get, or what you'll be able to analyze, is in 1D results over here. Remember, we have something called S parameters. So S parameters, in the case of this antenna, we only have S11. S11 is a representation of the reflection coefficient. The reflection coefficient tells us how much energy gets reflected back to the signal or to the feed, hence the name. So remember, in an ideal case, we want as much energy to get deposited at the end of this antenna as possible. So we want a reflection coefficient that is as small as possible, because remember, in the case that this antenna is perfectly matched, meaning we don't have any weird losses as a result of the antenna not being matched to its environment. So that means that for a reflection coefficient of 0, no energy is reflected back. We we transmit all of our energy in, and we get the best heating that we can get, which is of course our goal. So you have all of these S parameters. S parameters in CST are typically displayed in dB, although they don't have to be. Remember, the more negative the number is, so the more negative the dB is, the smaller the number is. Remember, small number is what we want. We want as small of a reflection as possible. So the way that parameter sweeps are useful to you is it will plot all of the parameter sweeps side by side in a plot of the S parameters. And so you can easily look and see at our target frequency of 2.45 gigahertz, which one has the smallest S parameters, or the smallest reflection coefficient. We say that an antenna is resonant at a certain frequency, or that its resonant frequency is the frequency at which it has the smallest reflection coefficient. And so that's what we can look at with parameter sweep. So now we're going to talk about the optimizer. The optimizer has the same goal in mind as the parameter sweep, which is to change the variables in a way so that your antenna or whatever you're modeling functions more the way that you want it to. The optimizer, however, does a little bit more work for you and is a little bit fancier. So let's go over this. So just like parameter sweeps, you'll have parameters that you can select. You can select more than one parameter to optimize at a time. However, in this example that I've said, we are just going to optimize gap. There are two ways that you can set the range, just like you did for parameter sweeps. You can either set it manually by double-clicking, or you can say, I want you to scale it. In my case, I did 100% of the initial value. The initial value is 1, so we get this range of 0 to 2. All right, what do we do with that? Well, we have to set a goal. And remember, I already articulated essentially what this goal is, which is we want the S parameter at 2.45 gigahertz to be as small as possible. So if we edit this, the way that so usually I said it's displayed in dB. You can display it in linear, it's just it has more meaning to me in dB at this point. And so the goal I've set is I want it to be less than negative 14 dB. Now when we come down here, there are a couple things, range and goal. And this is where I will point you to the documentation, because it's been a long time since I have used the optimizer tool in CST. But my understanding is you can optimize over a frequency range. We don't want to optimize over a frequency range. We want it to be optimized at our operating frequency of 2.45 gigahertz. And then it will define for you, or you need to define for it, how to choose the best one, how to choose what is optimized, quote unquote. And so I'm not sure what all of these different things mean, but maximum difference, my understanding is what is the farthest from our target. So in other words, if we do this parameter sweep of gap, it will choose the one that is the most small from negative 14. So let's say I got results of negative 14, negative 16, and negative 18. The gap sizes that produced a negative 18 dB S11 will be selected as the optimized, because I've defined it as the maximum difference. Now, I am going to point you to a lot of documentation to help you along the way with optimization. So recall, we have help contents. Such a beautiful thing. So in help contents, for example, of how you might get help on this, you could type in optimizer, and it will go into an overview of how does the optimizer work, what do goals mean, One thing I didn't really go over is there are different algorithms that you can use to do your optimization. Some work better than others. I am going to make the argument that because, at least in this example, and probably most of the optimization we're going to do on this project, we're only probably interested in optimizing one, maybe two variables at a time and over a pretty small range. Not to mention, we're optimizing at a single frequency rather than a range of frequencies. And so, because this optimization problem is relatively simple, I will make the argument that the algorithm probably doesn't matter so much. But I am also going to still point out that documentation is your best friend here. And so here's an overview of the optimizer. If we go back to our search results, we have overview of the optimizer, using the optimizer, defining goals, etc. So have at it. There are a couple other cautionary things I would like to mention, but we have at this point gotten through the gist of what optimizer and parameter sweep does. One thing, when you're running a lot of simulations back to back like this, one thing you're already looking at an extended simulation time. And so I just want to warn you about something that can happen. So I'm running a simulation right now. It's been running for a very long time now. And specifically, it has generated a lot of warnings. 17 last I checked. Specifically, it keeps saying current system memory usage has basically exceeded. If you exceed current system memory usage, your entire software will crash and you might even get booted out of the VDI. This is not what you want to happen. So why is this happening? Typically, it is because your mesh is too fine. So let's investigate this a little bit. So remember, if we go to the simulation tab, we can look at mesh. Remember, that's what's happening on a small level here is this has been subdivided into a bunch of little sections, and it's running calculations on each of those sections. And so you can see that if we go into this mesh view. So see all those little, each of these little individual squares, we are using electromagnetics calculations to do calculations. If your mesh is too fine, your simulation will take forever to run and it will consume a lot of memory. In the case of running parameter sweeps where you're running a lot of simulations, it is in your best interest to decrease the mesh view and sacrifice some accuracy. So for example, this is currently at about 4.2 million cells. Now, when you already know what your simulation values are and you want a really clean, high resolution, accurate simulation, this is appropriate. But when you're doing a lot of testing, so maybe you're running 8 different possible parameters, this will take forever and it probably will crash. The way that you can adjust mesh cells is by adjusting this cells per wavelength. So if we take it down to 10, say, see we're down to 1.2 million, which is reasonable, but we could probably do better. Let's see what 8 does. Whoops. 8, if I can open it, took it down to 684,000, so now we're below a million. There are some rules with mesh calculation. If you make the mesh too small, it won't be able to calculate the simulation correctly. Luckily, it will throw that error very quickly, so you can kind of do trial and error with this. But, as you can probably imagine what I am about to say, the help contents are ready and available to tell you anything you might need to know about mesh calculation. So let's do that and see what might come up. All right, so we have all of this stuff about how mesh works. Feel free to indulge in that lovely reading material. Okay, so to summarize, you can use parameter sweeps, which are a little bit less fine of a tool, but a little bit less difficult to use. You can use an optimizer, which does a lot of the work for you, but can run for a long time and requires you to understand how what the optimizer is doing in order to set up a decent optimization. And then finally, when you're doing optimizations, you need to be conscientious about the values you choose, so the range that you give it, and you also need to be conscientious about the mesh value. And remember that you can still get trends, you can still see what values look like they're going to be better, even if your simulation is not the most accurate thing in the world. So just make sure you check your mesh properties before you do the simulation. And then the last thing I want to bring up is, up to this point, we have discussed doing a coupled simulation. And by that, I mean we have these sub-projects, an electromagnetics project and a thermal project. All of the stuff that I've described here, optimizing in parameter sweeps, remember we're optimizing the S parameters, which is an electromagnetic result. It is in this EM1 subfolder, which is a CST Microwave Studio project. So all of this parameter sweep stuff, you don't need to do the update task coupled simulation thing that we've been doing up to this point. You can just run the simulations directly in this folder. To answer a potential question, which is, could I possibly do optimization or parameter sweeps in the thermal project? The answer is, why, yes, absolutely you can. And here they are. Oops. I feel like the climax of that statement got taken away a little bit. Anyway, yes, optimizers and parameter sweeps also exist in the thermal domain. We will get into that in a later video. Thanks for watching.